Hey folks, today we are going to talk about colligative properties of ideal solutions. And actually, colligative properties are only linked to ideal solutions. Ideal solutions are those solutions that obey Raoult's law over the entire range of concentration. Non-ideal solutions are not linked to the colligative properties at all. The what does colligative property mean in general, right? Colligative properties are a kind of properties that are related to the number of particles of solute that are dissolved in definite amount of solvent, but but these properties are not related with the properties and nature of the solute. They are only related to the number of particles of solute that are dissolved in a definite amount of solvent. The first property, or actually, there's no order in which the properties are arranged, but as far as we are concerned, first property is elevation in boiling point. What does that mean? Let me tell you. So, here I have made a comparison solvent and solvent plus solute. Keep in mind that solvent is volatile, solute isn't. This is one case that in which we only have the solvent. This is another case in which we have that very same solvent, but a non-volatile solute is added to the mix. What this property tells us is that the boiling point of the solution, the one with the solute, will be greater than the boiling point of the solvent itself, right? We have two solutions. In one we only have the solvent, and in the other we have the non-volatile solute and the volatile solvent. The boiling point of this solution, in which we have the solute and solvent together, will be more than the boiling point of just the solvent. This graph tells us here. This curve is for the solvent only, and this curve is also this curve is for the solvent and solute also. This on the y-axis we have atmospheric pressure. See, this is 1 atm, and on the x-axis we have the temperature. TB naught. This is TB naught. TB naught is the boiling point. TB naught is the boiling point of just the solvent. TB is the boiling point of this solvent plus solute. Of course, the TB is greater than TB naught, so delta TB, change in temperature, is TB minus TB naught. Pretty self-explanatory, right? But delta TB is also equal to ebullioscopic constant Kb times the molality of this solution, solvent plus solute. Alright folks, the next property that we have is depression and freezing point, which is pretty damn similar to the first one that we have studied earlier. As you can see, I made that the exact comparison over here as well. Over here we have just the volatile solvent, and over here we have that exact volatile solvent plus the non-volatile solute. But the story is a bit different here. The freezing temperature of just the solvent will be greater than the freezing point of the solution. Depression and freezing point. The solution's freezing point is less than the freezing point of just the solvent. It's as it's kind of opposite. This graph tells us exactly that. This is TF naught, this is TF. TF naught is greater than TF. TF naught is the freezing temperature of just the solvent. TF is the freezing temperature of the solution. And change in temperature, the delta TF is TF naught minus TF. The bigger value will come first. That's pretty damn self-explanatory. Delta TF is also equal to Kf. This is not a ebullioscopic constant. This is another constant. This is a bit different than ebullioscopic constant. This is cryogenic constant. No, it's cryoscopic constant. I'm sorry for that. It's a cryoscopic constant times the molality of the solution again. Okay folks, before going any further than this, I assume that you guys watching this video are familiar with Raoult's law and the derivation involved in it. So let's jump right into it. The third property is relative lowering in vapor pressure. In this property, we have a solution which has a volatile solvent and a non-volatile solute, right? So as we know that total pressure of the solution is equal to the partial pressure of component A plus partial pressure of component B. But as we know that as B is non-volatile, it will not involve in making any vapors and thus no partial pressure. So the partial pressure of component B is going to be 0 and P total is equal to partial pressure of A. And as we know that partial pressure of A is equal to the vapor pressure of A times the mole fraction. Total pressure, then if we open this, the XA, the mole fraction, we get total pressure is equal to PA naught times 1 minus XP. So we all know that mole fraction of component A plus mole fraction of component B is equal to 1. That's from that we can conclude this. Total, we open the brackets and we get this total pressure is equal to PA naught minus PA naught times XB, and we get to this. PA naught minus total pressure upon PA naught is equal to XB. But if we have the moles of B is extremely small when compared to the moles of A, we can neglect the amount of NB just from the denominator, not from the numerator, and we can conclude this equation right here. Next we're going to study about osmotic pressure, but first let's talk about what osmosis means. Osmosis is the net spontaneous flow of solvent molecules from a region containing less concentrated solution to a region containing more concentrated solution through a semi-permeable membrane. We have two types of osmosis, exosmosis and endosmosis. Exosmosis, let's take a look at this diagram right here. Exosmosis is when the semi-permeable membrane permits the solvent molecules to come out from a region containing less concentrated solution to a region containing more concentrated solution. That's why it's called exosmosis. It comes out, the solvent molecules comes out. In endosmosis is the process in which the semi-permeable membrane permits the solvent molecules to come inside of the region containing the more concentrated solution from a less concentrated solution. And next we have osmotic pressure finally. Let's take a look at this diagram right here. Osmotic pressure is applied at this on this solution. It's the minimum pressure that is applied on the concentrated solution that stops the flow of solvent molecules from this solution to this solution. It stops. Reverse osmosis. It's reverse osmosis is actually the it's a pressure that is more than the osmotic pressure. Any amount of pressure applied more than the osmotic pressure is leads to reverse osmosis. It means that the solvent molecules from the concentrated solution will move to the dilute solution from this semi-permeable membrane right here. And now that we have studied about the rise in boiling point and relative lowering in vapor pressure, the question arises that why do these two properties happen in nature? As you can see right here, we have in this jar just the solvent molecules, and in this jar we have both the solvent molecules and the solute molecules. On the surface, we only have the solvent molecules that are free to vaporize. They are not their way is not obstructed by any solute molecules. But in this jar, we do have the solute molecules that decrease the surface area for the solvent molecules to vaporize. So the rate of vaporization of this is greater than rate of vaporization of this. So hence we have the relative lowering in vapor pressure and rise in boiling point. If we heat both of these jars, you guys tell me which in which jar the vaporization will be faster. In this one, right? Because the surface area is completely uh, is complete for the solvent molecules to rise and vaporize, but not so in this one right here.